Okay, so my PPT is visible to everyone.
Yes, sir.
Okay. So today we are going to cover some case studies on vibration isolation. Now this is very important part, and we get numerous calls from the industry for vibration isolation problem, and we apply very simple concepts which we have learned in this course. In fact, this course we started in 2013 as an outcome of the industrial learning. Okay, so we will cover 3 case studies. So the first study, it came to us from the IT industry. So this is basically the building at a special economic zone in Gurgaon. So here this is office of and here software development happens, and also the office is operational 24 hours because they have to adjust to the US timings also. So this is one of the towers which reported problems. The occupants, especially when they are working in the night, they find vibration problem and they are not able to concentrate. And some of the staff members, they were reporting the problems of vertigo, giddiness. These kind of issues were also reported. So we went there, and especially we did the instrumentation using accelerometers on the locations which were reporting high vibrations. One such instrumentation I am showing here, and then one instrumentation we had installed on the specific tables, because some of the tables, they were reporting higher vibrations, and also the perception was different among different people. Some staff members, they said that they have never felt any vibrations in certain parts of the building, and in other parts, some of the staff members, they were very concerned that they feel something like earthquake kind of tremors, so they are not able to concentrate. So we did the measurement, and in fact very soon we could detect the signals. The disturbing signals were definitely there. So this is one of the typical signals. So how it occurred that it used to grow, and within a couple of seconds then it used to dwindle. So these vibrations, they were not continuous, but they used to come and then disappear. And we also did frequency analysis, and we found that there was a dominant peak of 13 hertz, and we convert it into RPM, that comes out to be 780 RPM. So this consistency was observed with regard to the frequency. Always the disturbing vibrations we captured at various locations, various times, and personally we could feel the vibrations. The vibrations were definitely there, and the consistency, what we observed was that they were always 13 hertz. So the typical duration was about 2 seconds. So with these observations, then we went further, and we found what should be the these measurements with regard to IS code provisions, whether they are exceeding or not. So we measured amplitude at 2 points. So at one point we found the amplitude was 66 microns, and at other location it was 90 microns, and at both the locations the frequency was 13 hertz. So we refer to IS 2974 curve. So this plot, so here we have the measurements of the two values, 66 microns and other 90 microns. I hope you are able to see these two lines, one conforming to 66 and other to 90 microns. And here we have the line approximately coming out at 13 hertz. So what we find that for one measurement 66, it is lying in between the two curves. So this line, it ensures reasonable comfort to the persons. So definitely the reasonable comfort to the persons is exceeded. So the 66 microns, that is exceeding this comfort, and basically it's lower than the discomfort zone. But the other one, the 90 microns, is just above the discomfort zone. But both the vibrations, they are within the limits of the structural these adequacy limit. So structural adequacy limit is here, the topmost, and then it bends like this. So the structure was not compromised, its integrity. So vibrations were definitely there. So from this chart we can conclude that in one case the vibrations, they are above the limit to ensure reasonable comfort, but then they are within the limit of serious discomfort to persons. And at one point, that was the AHU, air handling unit. So we recorded the vibrations as 90 microns, and this is certainly beyond the limit to avoid serious discomfort to persons. So any person who is in this particular location, he will feel adverse effects from health point of view also. So then we inspected the various machines which were operating, and we found some of the observations like this. Like this is a hanging kind of air handling unit, and this is basically directly connected with the roof. And similarly we found that a lot of such machines, they were resting on the floor slab. So floor slab of this building was very thick. It was a flat slab construction, so the slab itself was very thick, and all the machines, they were directly resting on the floor slab. The contractor, the vendor, he had not installed any padding in between the machines and the floor or the roof where they are hanging. So naturally here the transmissibility will be at least 100%. So if we assume that the floor is rigid, in that particular scenario the transmissibility is 100%, and if it has some flexibility, the transmissibility will be certainly greater than 100%. So that's the reason. And we made a check at the equipment. So the equipment involved this kind of rotating parts, where there were two rotors, and they were connected by a belt kind of mechanism. And when we went through the drawings, we found that their operating frequency was 849 Hertz as per the drawings, as per the specifications, and this is something 14 Hertz, which is very close to the disturbing frequency which we had captured. And similarly this is another machine. So here we found the drawing had listed the operating frequency, the RPM as 867, and that is also close to 14 Hertz with some decimal places. So this basically gave us the credence that these vibrations, they are resulting from these machines, from the matching frequency. Now at some points, some places, the frequency was different, because those vibrations, they were operating at different frequencies, like the packet air conditioning unit for the UPS, and there we measured the dominant frequency as 30 Hertz, and the amplitude was recorded as 27 microns. Now this frequency is higher than 13 Hertz, 13. So as we see the curve of IS2974, so higher the frequency, then there is a lower limit for comfort, discomfort, and for structural safety. So what we found that this 27 microns at 30 Hertz, so it is beyond the limit to ensure reasonable comfort, but of course within the limit for avoiding serious discomfort to persons. So then the next was what remedial actions are needed. So first of all, we advised them to carry out all the servicing of the machine. So the company, they carried out all the servicing. So as part of the servicing, they did cleaning of all the dirty and clogged filters. So this was one of the measures. The company found that the filters were clogged and they were cleaned, and then the tension in the belt that connected the two rotors, that was also adjusted, and that was tightened. The belts were replaced. So these measures were taken, and then the next was to install the paddings, because there was no padding found. So we designed the padding. So from the data of the machines, we have the mass of the machine, and we have the other details. So we calculated the transmissibility. So if we assume that damping is 0, ignoring damping, we get a simplified relationship. So all we need is the natural frequency of the system. So we assume that the resting point is rigid. So we have these rubber pads. So we can calculate their stiffness. We have already learned. So from the stiffness and the mass of the machine, we can find out the natural frequency, and we already have the operating frequency of the machine. So from here we could calculate the transmissibility. So we adjusted the size of these blocks such that we are getting transmissibility very low. And how we do it, we increase the frequency ratio. So the frequency ratio, for example, we found the frequency ratio from our design, it was coming out to be 3 point something. So it's definitely greater than √2. So it's fine. And for this particular frequency ratio, the transmissibility will be less than something 12%. Similarly, at other points, we designed these kind of support. Now you see what we have done is that we have made this special kind of padding. So it has a rubber. So rubber acts as the spring, and at the top and bottom we have felt layers. So felt layer offers damping, though in the calculations we are ignoring damping, but there will be damping also, and the effective transmissibility will be something less than 5%. That's what we estimate with this. And I'll just show you one sample padding. So what I am doing is that I am just minimizing the presentation for the time being, so that you can just see the rubber padding. So just bear with me. So now I am just keeping this in my hand. So do you see this kind of system? So what we see here, this is the felt layer. So other day also I showed you the felt layer, how it looks like. So I hope this is visible to you in greater clarity. So this is the felt here, and then we have the rubber, and then again the layer of felt. So two layers of felt, and in between the two layers we have sufficient depth of the rubber as per our calculations. So I'm just coming back to the presentation.
So I was not able to see the rubber.
You can always see the recording, so you just
Okay.
bear with that. Yeah.
Okay, sir.
So you are now we are back at the presentation. So we designed for different machines because their masses were different. So according to the mass, we tuned these we tailored, rather not I won't use the word tune. We tailored these paddings such that we are getting frequency ratios, they are quite high, so that transmissibility is very low. So this is another case where we are getting a frequency ratio of 2.75. Yes?
Sir, we are not able to see your presentation.
You are not able to see the presentation?
No, sir. We can see you.
Screen has freezed.
Okay, let me do again. Now can you see the presentation?
Yes, sir. Yes, sir.
Alright, so we were here. Yeah, so different machines were there, and each had different masses. So accordingly we did tailor we tailored the dimensions of the rubber paddings so that we are getting sufficient value of the good value of the transmissibility, which is very low, a low value of transmissibility. And for different locations, we adjusted the dimensions. For example, here the value of the frequency ratio is 2.75. So here the transmissibility will be different, but of course very low transmissibility. And after these remedial measures, we again went there say 1 month later, and we did the measurements for about 24 hours, both day and the night. And what we found that now there were no detectable vibrations at those locations. For example, at this particular location, earlier we were observing vibration amplitude of 90 microns. There was no adverse vibration detected, and similarly at the other location where earlier 66 microns of vibration amplitude was detected, now nothing was found. So the client was very much satisfied, and these measures, they had borne the fruit. Now the other case study I would cover is this building. This is a building in Connaught Place of Delhi, and they had also reported almost same kind of problem by the staff. So this is the headquarter, and here this is also working 24 hours because there are servers. So all the transactions, online transactions, they are monitored from here centrally 24 hours of the day, and staff, they keep working, and they also reported similar kind of vibrations. So when we went there, and the first observation was that all the steel frames, they were resting directly on the floor slab. So it was a suspended floor, about 1 meter suspended floor. So if you walk on the floor, you would feel that you are not walking on the concrete floor, but on a sort of suspended floor. It will make noise also, and it will cause disturbance. And because the suspended floor was supported on steel structures like this, so not only the machines, but the suspended floor was also supported on these steel frames. So steel frames, they vibrate, slender members, they had vibrations. So even the walking was creating vibrations, but walking was not a problem. But the main problem was that the staff, they were reporting rhythmic vibrations, just like the earlier case study. So what we found was that at one point where we found the frequency was 49 hertz, the amplitude what we measured was 42 microns. And now here we have the chart, and at around 50 hertz I am drawing the line. So 49 micron 42 microns is somewhere here. So definitely it's even sort of exceeding the limit for the safety, structure safety also. So we did measurements at various locations in the building, and because of the floor slab was the false floor was there, and all the machines, they were supported on steel frames. So we found that the vibrations, the level was much higher than the permissible values. So for example, at 42 microns of measurement at a frequency of 49 hertz, so the permissible values are 7, 15 and 36 microns to ensure reasonable comfort, serious discomfort and potential damage to the building. So what we find that the magnitude was quite high, and we immediately alerted the authorities that very urgent action is needed, because here not just the comfort of persons, but here the integrity of the structure is also doubtful. And we also measured horizontal displacements, and at some locations this was found to be in excess of 80 microns. So then the next issue was that we contacted the manufacturer, and we asked for the data of the these rotating and the vibrating machinery. So what we found that they provided us the data that the compressor was operating at 48 hertz, the motor at 24 hertz, and the fan at 13.5 hertz. And from the measurement, we could very easily correlate these frequencies, because we found the peaks which are very much close to these frequencies of the 13.5 hertz, 24 hertz, and 48 hertz. So these disturbing signals were detected in the building, so we could very easily point the source. So the source was that the compressor, the motor, and the fan. And it was also found that these machines were quite old, and then we requested immediate servicing, and we also proposed that we will design the paddings, and immediately the machines, they should not be rested directly on the steel frames which are directly connected to the floor slab. So this was also an issue that the machines, they were resting on the steel frame, and the steel frame members, they were slender, so the vibrations were very easily transmitted to in far off places, because in steel there is hardly any damping. So here the transmissibility of the floor was also very high, because there was no rubber padding in between the machine and the frame, and the floor slab also acts as the medium for transmission of the vibrations. In fact, when the people or the staff, they are walking, and especially if we tend to walk with heavy steps, then these would also induce mild vibrations, but they were not much matter of concern. But the machines, they were definitely matter of concern. So we recommended the client that the machines should be serviced immediately, and especially the compressor, because the disturbing vibrations, what we found was the ones at 49 hertz, and they were because of the compressor. So compressor should be serviced on a urgent basis. That was our suggestion. And then we also designed the rubber paddings for bringing the spring action, and we recommended that the machines, they should be supported on isolation pads, and we designed similar kind of paddings for their machines like this, so that the machines, they are rested on these paddings rather than directly on the frame. But the manufacturer, he had some reservations that this would affect the stability of their machines. So we suggested that we can also recommend continuous padding all around. So these were also recommended. So both options were given, and we also suggested that there should be discontinuity or gaps in the steel frame, so that the vibrations of one particular zone, they are restricted to that particular zone only. They are not transmitted to far off places. So these recommendations were made to the client, and what we learned was that the client, they worked with the manufacturer to replace the machines. The machines were very old, and they then most likely they replaced the machines. Though from our side, we had also given them the solution of these paddings, which could work with the existing machines also. Now the third case study is a very recent one, and this came from this building. So if you go to if you take the magenta line of the metro, which passes through IIT Delhi, then this magenta line, it passes just below this particular building which reported problem. So here just outside this building, there is a metro station also. So it is a reinforced concrete structure, and there is a basement also. So the ground floor is basically a suspended RC floor. It's not resting directly on the ground. So what they reported was that they were the staff were finding earthquake-like vibrations, intermittent vibrations, and most of the vibrations, they were found at two places: 7th floor and the 1st floor. And also they were also found in the reception area, the ground floor. So first floor, there is the office of the chairman and the managing director. So personally, the CMD also reported feeling vibrations. So that's why we were referred to this problem. So this basically the company is the Telecommunications Consultants of India Limited, public sector undertaking, and it does the consultancy services for both Indian and overseas clients. So we started with the measurements, and we did beginning from the reception area. So this is the floor. Later on I'll show you the larger picture also. We are just showing here the region near the accelerometer, and we did the measurement, and at the same time you see here basketball. So this we had brought for the purpose of doing a controlled vibration test, just like we have the impact hammer. So here we do this kind of testing so as to excite the floor slab with our vibrations, so that the floor, it vibrates at its own natural frequency, and we could measure the natural frequency of the floor slab. So we found that the natural frequency of the ground floor was measured at 88 Hertz, and this was when the disturbing vibrations were not there, and we also measured the disturbing vibrations. So we found that the frequency of the disturbing vibrations was 24 Hertz. Now here there was a contention. The view of the management was that the metro line is installed. The metro had started functioning just couple of months before, and they were anticipating that it is because of the operation of the metro these vibrations are coming. When the trains are passing through, the braking action is there, that time the earthquake like vibrations are happening, and rest of the time they are not happening. So that was their contention. So what we found that here the vibration frequency was 24 Hertz, and at several locations we measured the vertical displacement also. So we found that at 24 Hertz the measured displacement of 30 microns, it definitely exceeded the limit of reasonable comfort to persons. But yes, it was below the other limit of serious discomfort. So most of the time we could find the frequency was 24 Hertz, and this is now shown here from this frequency plot. So this is now the bigger picture, where you see the entire team. Dr. Dhawan was also in the lead because he has a lot of practical experience also. So this is the ground floor area near the reception, where we started with the measurement, and this reception is itself a floor, though it's at the ground level. So there was a basement also. So we were very curious to know what's in the basement. So we found that basement, basically it was the place where all the machines, the machines which were related with the air conditioning system of the building, centralized air conditioning system, they were operating from the basement, just below the point where we are standing. So this is the floor vibration test using this ball as an exciter. And then we also did measurement on the 7th floor. So 7th floor we did both vertical and horizontal measurement, and on 7th floor we found something very interesting, that we found that it's the floor's natural frequency was 5 Hertz. We did by excitation with a chair and also with football, and at one instance of vibration we found the displacement of the top floor was in the horizontal direction, came out to be 1.5 microns, and the frequency was measured at 192 Hertz. So we can see here both the time domain response and the frequency domain response. So it was like this, that suddenly our staff who was there to record the vibrations, he felt the tremors in the horizontal direction, and when we analyzed the signal we found 192 Hertz. Now this 192 Hertz is also related to 24 Hertz, It's basically, if you multiply 24 Hertz by 8, it comes out to be 192 Hertz. So essentially this 192 Hertz is also a higher harmonic of the 24 Hertz main signal. So we found again the suspicion that there is something 24 Hertz. So what is the cause? So we went down, and also we had the apprehension of the metro. So both the metro as well as the machines, they were possibly the source. So we first measured the operating frequency of the machines. So here we are showing the instrumentation. So this is a motor, and on the top of the motor we have installed the accelerometer in the vertical direction, and then there is another machine where we are showing the accelerometer in the horizontal direction. So this is the AC plant, and here most of the machines, they were operating at frequencies of 24 Hertz, and the vibration of the floor itself was measured as 44 microns, and definitely this was above the limit of the serious discomfort. So anyone who is working in the basement, he would not be able to work for longer duration of time. And now we are showing you some of the clips of the measurement. So here Dr. Sumit is there, and which is set up in the basement. So basement area was very hot, humid, and it was a bit difficult to record the measurements. And here Dr. Dhawan is also there, and Dr. Dhawan, he recommended measuring the vibrations of this pipe. So this pipe was vibrating heavily, and this pipe was going to the top floors, because all the air conditioning ducts, they go all across the height of the building. So it was going till the top. So it is a potential source of transmission of the waves. So these are some of the clips of the measurement, and this is also a picture of one of the machines, possibly compressor. And here Dr. Smith is also using his hand to feel the vibrations, and the vibrations were definitely heavy. And here is a screenshot of the vibrations which we measured. So they were quite strong vibrations, and possibly these were going up and creating secondary vibrations. So here this is the floor, and here you can see something like a trench barrier, something very shallow trench barrier like construction, but it was also not very effective, it seems. So what we found from the measurement at the basement, we found that on the machines the vibration amplitude was as high as 128 microns, and this could be detrimental for the operation of the machine also. And on the pipes, we found that on one particular pipe the amplitude was 161 microns, and definitely this is exceeding the safe limit for avoiding structural damage. So our general impression was that machines were, of course, emitting vibrations. Their vibrations were exceeding the limits, but the other was metro. So we had to study the metro, and then the other finding was the pipes, they are going up, so they are also carriers of the vibrations to the higher floors. Now the thing was, how do we assess metro? So before going to metro, undertook a major servicing of all the machines, and then once this was done, we went there, and next object was for the metro related vibrations. So for metro, we decided that what we'll do, we'll take the measurements in different situations. Let's say we have the control of the AC unit, so we can switch off the AC unit for some time, because at the night when the office is not working, and they agreed that for 1 hour or 2 hours, say 12 o'clock onwards, they would switch off the air conditioning unit. So at that time there is no metro and there is no air conditioning unit also. So we would take measurements at that time. And then during the daytime, metro is also operating and the air conditioning unit is also operating. So we would record the vibrations at that time also. And during daytime also, we can temporarily switch off the AC unit, and when the metros are passing through, so that can be recorded. So we selected different time zones because they had the office timing. So after the office closes, so metro keeps operating till 11 o'clock. So we had sufficient window. So we decided that we'll do like this, that when the metro is operating, but the AC plant is also operating. So this measurement we took at 8 p.m. in the night, and then we requested them to switch off the AC plant. So we took the measurements when the metro is operating, it's passing below, and the AC plant is switched off. And then we took the measurement when metro is also off and AC plant is operating. This is at 2 p.m. and then metro is also off and AC plant is also off. So this is at 3 am. So different these situations were considered. So what we found that under number 2, when the metro is operating and the AC plant is off, so at that point of time we did not find any noticeable vibrations. And not just at the basement, we did these measurements at various locations of the building. But when the metro was operating, AC was off, at that point we did not encounter any noticeable vibrations. But of course, when the two are operating together, then of course there is vibration. But this measurement when the metro is operating and the AC plant off and there is no noticeable vibration, so this totally eliminated the case of the reason being the metro. So that was the main finding, and we can summarize the conclusions. So we found that the main source of the disturbing vibrations were the machines in the AC unit located at the basement. 24 Hz was the operating frequency, and there was no evidence of the metro induced vibrations. And basically metro operates at very large depth, more than 30 meters, and metro does take suitable measures so that the vibrations are not transmitted to the ground floor level. They are basically they are ending within the soil itself. And then we found that at some locations the amplitude of the vibrations, it was exceeding the limit to ensure reasonable comfort to the occupants. Some places it exceeded the reasonable discomfort limit, and at certain locations such as the pipes, it was much beyond the structural safety. So definitely the pipe could also break on account of these vibrations. And we found that the resonance frequency of the ground floor, it is fortunately away from the operating frequency of the machine, so it's not near the resonance. So we have frequency ratio quite away from the resonance. And but the 7th floor, it is dangerously close to the operating frequency of the machine. 7th floor, the natural frequency was measured as very close to the operating frequency of the machine. So that was something which could create more problems. So what we recommended was that they could get all the machines inspected from the manufacturers, and we also offered them that if they want special these paddings designed, they could we could also design that, but they have done it through their manufacturers only. And another observation was that pipes and conduits, they can also transmit the vibrations to very long distances. So necessary isolation measures are required for these components also. So thank you very much. So if you have any questions, you can now ask any questions related to these studies. So these studies, they are from the in-house conducted studies, and this is a very important area. There is lack of expertise in the measurements and interpretation of the vibration related problems. So here all these 3 buildings, they were basically office buildings, and of course there are problems from the plants also. And we have we've been called for those plants also. One problem we have been approached, and that's involving the trench barrier. So there's a problem that the vibrations are happening, and despite the presence of the trench barrier, the vibrations, they are being transmitted to the nearby buildings, and those buildings are vibrating. So now I think you have any questions, you can raise your hand. So Dr. Dhawan, would you like to add something for the benefit of the students?
Excellent presentation, sir. My message to them that they can get some time and go and see. The places where you have explained that you took measurements by putting accelerometer, and then you have been getting different frequencies and the displacements. And then they should go through this code also, which you have specified.
Yeah.
And make conversion themselves to this table, whether vibrations are within a comfortable zone or not. So it has been really great opportunity for them to know that vibration can cause discomfort and can cause damage to the structure. So they can go and see, particularly near this GK2 TCL building, which is very near to the office, where they can go and see that the movement of the AC plant and the motors, how they can cause disturbance and can further damage to the structure.
Yeah.
Very nice presentation. Thank you.
Yes, so in the regular semester we have a field visit, also a compulsory part of the project, of the course. In 2019 we went to NTPC Dadri, and the students, they took the measurements and they could feel the vibrations of the turbo generator deck type building. So but unfortunately here in the present pandemic situation, we have to just rely on these virtual visits only. Hope the situation would improve, but as of now we are not sure of the next semester also, because now the situation is repeating as for the last year. All the cases are now rising. So earlier it was Maharashtra, and then now Kerala, now Delhi is also picking up. So the 10 districts, they have been identified, and Delhi is one of the hotspots of the coronavirus, and already now in the campus, our campus also, the cases are increasing. So I'm not sure of the next semester, but if you got chance, so please try to look around yourself and see the vibrations and feel the vibrations. So any question, if you have, you can just raise your hand. Yes, Narinder.
Sir, in the last study, case study 3, we have concluded the vibrations are not due to the metro, and the pipes are a source which are transmitting the vibration. So have we also recommended something like what should we do, or it was out of our scope, like something like isolating the machines or providing rubber pads like this?
Yes, so we had done this project in 2 parts. So the other building, we had done the part 1. Part 1 was to isolate to identify the source, and part 2 was the remedial measures. So here the remedial measures was not in the scope of IT, so or scope was just to identify the source. So otherwise we had offered them remedial measures also, depending on the particular machine, but they said that their own internal departments would do that.
Okay, sir. And in case study 1, you have mentioned something regarding the belts, which transmits the energy or power, something like that. That there was not enough tension or they were highly tension. I didn't get that thing. So can you please explain that
Oh yes. So for this,
in case study?
have you ever seen the flour mill where you take the wheat to grind into flour?
Yeah. Yes, sir.
So if you go to such these flour mills, you will notice that there's a belt which is the motor is connected to a belt, and from the motor the torque is transmitted to the other rotor through a belt. Okay, so this belt is very crucial. So if the belt it loses the tension, then it creates losses for the transmission of the torque and the power from from the motor to the grinder. That is one thing, and also it creates unwanted vibrations. Now these belts you can see in the cars also. I had earlier Maruti 800, and when there's a belt in the mirror in one of the rotors in the if you open the bonnet, there is a belt which rotates some part, and when the belt gets loosened, the car starts emitting a noise, a very shrill noise, and it also starts creating the vibration. So there also is the problem of the belt. So if the tension is not proper, it will create unwanted vibrations.
I have got some more experience about the car. See, I have been going on inspection and traveling 400 kilometers distance. And as you said, this belt, we used to keep 2-3 belts as spare with the driver, so that at the time of problems, which you have explained, we used to replace the belt so that there will not be vibration.
Yes. Yes. So this was very common in the cars, even in Maruti 800. I'm not sure what mechanism is there in the new cars, but this.
In our time, ambassador car was there. Sir.
Yes, ambassador cars. Yes, ambassador cars was also there.
This belt facility.
Yes, definitely. Dr. Dhawan has given a very nice example. And Asif, you also have some question?
Yes, sir. My question was related to the experiment number 4, which you had provided last week.
Experiment number 4. Okay, it is okay. Does anyone have any question related to what we have covered today? We'll first cover today's session, then we'll come to the experiment. So no question. Yes, now you tell, Asif.
As you told us in the tutorial problem that when the center CG of machine, pedestal and footing lie in the same plane, then definitely the CG of the whole system will also lie in the same plane. So when we calculated 5y, that was about the CG of the system, and we transferred that to the base of the footing, that was 5y naught, by adding mz square. But in the case of experiment 4, I can see that there is a shifting of the center of mass of the system towards left. So in that case, when we will definitely we will try to find 5y about the system, but when we will transfer that to the base, so will that base be located right beneath the CG of the system or at the middle of the footing, sir?
Yes, this is very important, that the CG of the base and the CG of the block, they should lie in the same vertical plane. And maximum we can permit an eccentricity of 5%. Otherwise, the vertical vibrations will also, vertical and rocking will be coupled. Okay.
In that case, sir, then the moment of inertia Iy which we find, then we will have to use parallel axis theorem also.
Iy, why you use the parallel axis theorem?
No. If the base is just beneath the CG of the system, then I don't think we will need that. But if the base of the system we consider at the middle of the footing, then it will be required to.
See, Iy is with respect to the CG of the base, and you make sure that CG of the base and CG of the main block, because you have now different components, you can find out the CG in the plane. So those, they should lie in the same vertical plane. Okay, so you find the CG of the block, and then you also keep the base such that both are coinciding. Okay, so the Iy you have to take about the line passing through the middle of the base. Alright. Okay, so any other question you can ask as we just take the attendance.
And sir, another thing, does yawning take place about the axis passing through the CG of the system?
Sorry, I could not understand.
Yawning takes place about the CG of the system passing about the axis passing through the CG of the system. Since the CG of the system is shifted, so the yawning will also take place about that axis only.
Yawning basically it's in the plan. If you now, yawning takes place about the vertical axis. Okay, so vertical CG, I mean in the vertical axis passing through the CG of the whole system. Okay, so we have the you make sure that the vertical axis is such that it is passing through the CG of the block portion and also the CG of the base slab. So yawning will take place about this axis.
Thank you, sir.
Alright, fine then. So we'll just take the attendance. I think we don't have time for attendance now. So anyone is absent? I think Manish Kumar Meena, are you there? I think Manish Kumar Meena is only absent. Rest all are present. Okay, I think we can now end the class. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.